The global building sector currently generates nearly 40% of energy-related CO2 emissions. To meet strict decarbonization targets by 2030, the industry is transitioning away from concrete dominance toward biogenic materials, specifically high-rise mass timber. Scaling timber structures up to 10 or 15 stories is a solved engineering problem. However, pushing engineered wood past the 70-meter vertical threshold breaks standard structural assumptions. At these altitudes, engineers are constrained by the physical properties of wood. Timber lacks the extreme compressive mass of traditional concrete, and it does not possess the high ductility of steel. Reaching 80 meters and beyond requires abandoning pure timber topologies. Instead, structural engineers rely on highly optimized hybrid systems to manage forces that traditional wood framing cannot handle alone. The 86.6-meter Ascent building in Milwaukee stands as the current height record for this hybrid approach. By utilizing approximately 7,200 cubic meters of engineered wood, the Ascent Tower acts as a massive carbon sink, sequestering roughly 7,200 metric tons of CO2 equivalents over its service life. In Norway, the 85.4-meter Mjøstårnet tower provides the primary structural counterexample to Ascent's design. These records are corroborated by other regional case studies, including the 84-meter Ho Tower in Vienna and the 73-meter Hout in Amsterdam. By dissecting the structural data from these specific towers, we can extract the new universal benchmarks for high-rise timber engineering. Sustainable density results from re-engineering how existing biogenic materials handle lateral loads and fire physics at extreme altitudes. The core aerodynamic problem with tall timber is a matter of mass. Wood's high strength-to-weight ratio allows it to perform exceptionally well in seismic events, but its low dead mass makes tall towers highly susceptible to severe wind-induced sway. Ascent's baseline solution identifies the dominant global model for tall wood, the hybrid RC timber system. In this model, gravity loads are handled by a glulam post and beam grid paired with one-way spanning CLT slabs. Glulam, or glued laminated timber, is an engineered product made by bonding layers of lumber together, while CLT, or cross-laminated timber, consists of wood panels glued at right angles to maximize rigidity. While the timber manages gravity, lateral stability is strictly outsourced to the central reinforced concrete, or RC core, which houses the building's elevators and stairs. Ho Vienna mirrors this methodology, docking a prefabricated timber structure directly to a rigid concrete spine to prevent wind deflection. Mjøstårnet, however, proves that a timber-dominant lateral load solution is mathematically possible. Instead of relying on a central concrete core, Mjøstårnet's primary load-bearing system utilizes massive perimeter glulam trusses to maintain structural rigidity. These exterior diagonal members are engineered to resist both horizontal wind shear and vertical gravity forces simultaneously. To achieve this autonomy, the dimensions must be scaled. Mjøstårnet's corner columns reach a cross-section of 1485 by 625 millimeters. Even with trusses of that size, high-altitude sway remains an issue. To solve it, engineers introduced a concept known as mass injection. For floors 12 through 18, the design abandons timber decks entirely, replacing them with 300mm thick composite concrete slabs. This top-heavy mass acts as a dampener, stabilizing the structure's weak axis to eliminate wind-induced vibration and meet habitability comfort criteria. In Amsterdam, the Hout Tower uses CLT shear walls reinforced with a steel tension ring that runs the height of the wall to transfer diaphragm forces. Securing lateral stability 80 meters in the air requires either a concrete core, massive exterior timber trusses, or composite tensioning. Structural engineers manage high-rise timber as a composite discipline, using concrete and steel to strategically compensate for the material's lack of mass. Across all 4 benchmark projects, the material specifications have converged into a consistent, reproducible global standard. The data shows a strict baseline. High-strength glulam, specifically GL28 to GL32 grades, is used for load-bearing columns, while C24 grade CLT, ranging from 160 to 240 millimeters thick, is standardized for floor panels. Erecting an 80-meter tower out of these materials introduces a severe logistical hurdle, the complete elimination of on-site cutting or modification. This requires off-site CNC machining. CNC stands for Computer Numerical Control, a process where pre-programmed software directs factory machinery to carve wood with extreme accuracy. This industrial prefabrication shifts labor from construction sites to controlled factory floors. Looking closely at the micromechanics of these joints, the beams are secured using internal slotted steel plates, combined with acid-proof steel dowels. These steel connections are deliberately hidden within the wood envelope. This placement protects the steel nodes from environmental moisture and insulates them from intense heat in the event of a fire. Because of this internal hardware, the required tolerances are absolute. Every structural beam arrives fully processed and must fit to the exact millimeter on the first try. The Mjøstårnet project data provides the ultimate proof of this efficiency. Out of hundreds of massive glulam components delivered to the site without any prior factory trial assembly, only a single diagonal piece failed to fit perfectly. Modern timber construction functions as a high-stakes manufacturing process, where structural integrity relies on zero-tolerance alignment. All of this precision raises a professional paradox. How do buildings made entirely of combustible fuel achieve legally mandated 2 to 3 hour fire ratings? Untreated wood exposed to severe heat reacts immediately, blistering and degrading. Fire safety relies on managing how the material burns, rather than attempting to prevent ignition entirely. Instead, engineers rely on the material's primary structural defense strategy, sacrificial charring. Softwood glulam undergoes pyrolysis, the thermochemical decomposition of the wood at high temperatures, at a highly predictable rate. According to Eurocode 5, this notional charring rate is approximately 0.65 millimeters per minute. The resulting layer of black char has exceptionally low thermal conductivity. It acts as an insulating, fireproof blanket that protects the unburnt interior wood from the heat of the flames. By calculating this burn rate, engineers intentionally oversize the structural members to account for the exact section loss, while adding a 7 mm zero-strength buffer zone just behind the char layer. After 120 minutes of fire exposure, a Mjøstårnet column loses roughly 85 mm per face. But because of this sacrificial oversizing, its unburnt core safely carries the building's full load without buckling. This strategy is supplemented by encapsulation. In the Ho Vienna Tower, the upper facade is wrapped in non-combustible fiber cement panels to prevent exterior fire spread between floors. Fire safety in timber high-rises embraces the material's combustibility, mathematically weaponizing its predictable charring properties to create a verified structural defense. Pulling the data points from Ascent, Mjøstårnet, Ho, and Hout gives us the definitive tall timber blueprint. This method operates as a highly optimized hybrid discipline, utilizing concrete cores for sway control, hidden steel nodes for joint security, and CNC manufacturing for absolute tolerance. By mastering all of these unique benchmarks, engineers are slowly shifting timber toward greater structural autonomy in the vertical landscape. These landmark towers act as definitive proof of concept, providing hard data to satisfy performance-based design codes globally. The measured performance of these towers confirms that the carbon-negative skyline is a buildable reality.